In our project, we address the problem of using machine learning techniques to correctly identify command words. Our data set is the Google speech commands, which contains approximately 100,000 audio files of people speaking single words. The dataset contains 20 core command words, which most people speak 5 times. It also contains 10 auxiliary words, which most people speak once. For feature extraction, we used MFCC or mel frequency cepstral coefficients, which are a representation of short term power spectrum of a sound based on linear cosine transform of a log power spectrum on a nonlinear mel scale of frequency. We first convert the audio files to MFCC features by leveraging the Librosa API and then use these 2D MFCC features to train our models. Before neural networks became so popular, HMMs were used increasingly for speech recognition. This model belongs to a class of stochastic signal model that contains n states S1 through Sn. Each state can have m observable symbols V1 through Vm. Each observable symbol can be drawn from a PDF, such as a mixture of Gaussians. The model parameter B is the probability of observing Vk at time t given that state at time t is equal to Sj. The state transition are given by Aij. It is the probability that state at time t plus 1 is equal to Sj given that state at time t is equal to Si. The initial state distribution, pi of I, is the probability that state at time t equals 1 is equal to Si. Given model parameters n, a, b, and pi, HMM can generate observation sequences O1 through OT. Given an observation sequence and a model lambda, we can compute P of O given lambda by summing the joint probabilities over all possible states. Training an HMM uses expectation maximization technique we learned in class. Here, we adjust model parameters to maximize P of O given lambda, and the model parameters are given below.
We also investigated the efficacy of using multinomial logistic regression with the softmax function. And finally, we trained a convolutional neural network. The input was the number of examples times MFCCs times time times a depth of 1. The difference between a convolutional layer and a normal, fully connected layer in a neural network is that a neuron in the convolutional layer is only connected to the elements of the previous layer that are in its receptive field, and not all the elements. This helps the network to be deeper while having fewer free parameters. The CNN also uses pooling, which is a way to downsample the inputs and simplify the computations. The hidden layers used ReLU for activation, and the output layer used softmax. We use cross-entropy loss function. Shown below are confusion matrices on test sets for 3 of our models. The first two use HMM with mixture of Gaussian for underlying probability of the observable symbols and states. The first one of those is trained on numbers 1 through 10 using the dataset. Note that the diagonal entries correspond to correctly classified examples, whereas off-diagonal entries are ones that our model failed to identify correctly. The second one is trained on the remaining 10 command words from the dataset. Its test performance is comparable to the model trained on numbers. Our final model uses the CNN and has much better performance than HMM-based models. The multinomial approach was significantly less successful than the other 2 models we trained, with approximately 23% accuracy. We were able to achieve 65% accuracy using the HMM-based models. So we observed that our precision recall was comparable. However, based on training and test set accuracy, we still have a large bias in our HMM model. We also trained a simpler HMM using recordings of our voice and did perform much better with an 83% accuracy. We believe the increased accuracy in this model is due to the fact that the simple HMM models were not able to generalize to different people's voices, as well as it can perform on a single person's voice. Our CNN model achieved 90% accuracy on the test set containing 8,000 examples. To put this in perspective, Google in 2017 boasted under a 5% word error rate. Based on this study, we believe the HMM-based models have potential to work well for small vocabulary-sized data sets over a handful of speakers. Perhaps this is more suitable to edge devices. However, due to the high expressivity of neural networks, CNN-based models achieve high accuracy on large data sets over large numbers of speakers. We hope to provide detailed error analysis for our models before turning in our final report.